Padmakant Dhage, Assistant Professor, Electronics and Telecommunication Engineering, Walchand Institute of Technology, Solapur. My topic is thumb instruction set. In that, we are going to see branch data processing stack software interrupt instruction in ARM7 embedded system. Learning outcome: at the end of this session, student will be able to explain the thumb concept, 16-bit thumb set, thumb's advantages, thumb register set, thumb instruction set in ARM7 embedded system. Contents: explain the thumb concept, 16-bit thumb set, thumb's advantage, thumb register set, thumb instruction set. At the end of this session, student will be able to understand the thumb concept, 16-bit thumb set, thumb's advantages, thumb register set, thumb instruction set in ARM7 embedded system. The thumb concept: the ARM7 TDMI processor employs a unique architectural strategy known as a thumb, which makes it ideally suited to the high volume application with memory restrictions or applications. Where code density is an issue, the key idea behind thumb is that of a super reduced instruction set. A 16-bit thumb set. As shown in diagram, 16-bit thumb instruction set. The thumb set's 16-bit instruction set length allows it to approach twice the density of standard ARM code while retaining most of the ARM's performance advantages over traditional 16-bit processor using 16-bit registers. Thumb code is able to provide up to 65% of the code size of ARM and 160% of the performance of an equivalent ARM processor connected to a 16-bit memory system. As shown in diagram, add R2, R2 hash 1, that is the 32-bit ARM instructions, while add R2, hash 1 is a 16-bit thumb instruction. Core has an additional execution state, that is thumb, which is used for the switches between ARM and thumb using BX instruction. For most instructions generated by compiler, first one, conditional execution is not used, second one, source and destination registers identical, only low registers used, constants are of limited size, inline barrel shifter not used. Thumb advantages: the thumb has higher performance than the ARM on a processor with 16-bit data bus. Thumb has higher code density, the space taken up in memory by an executable program, than ARM, and allow faster performing ARM processor in some cases to replace the traditional combinations of processor plus a DSP, that is digital signal processing. Major advantage is its ability to manipulate 32-bit integers with single instructions and to address a large address space efficiently. Overall memory footprint is reduced even though the thumb instructions use for more instructions. Thumb register uses, as shown in diagram of register and access. In thumb state, user do not have direct access to all register. Only the low register R0 to R7 are fully accessible, as shown in table. The higher registers R8 to R12 are only accessible with move, add or CMP instructions. CMP and all the data processing instructions that operate on low register update the conditions flags in CPSR, that is current programming status registers. There is no direct access to the CPSR or SPSR. In other words, there are no MSR and MRS equivalent thumb instructions. To alter the CPSR or SPSR, user must switch into ARM state to use the MSR and MRS instructions. There are no coprocessor instruction in thumb state. User need to be an ARM state to access the coprocessor for configuring each cache and memory management. thumb instruction set. First one branch instruction, second one data processing instruction, third one stack instruction, fourth one software interrupt instruction. First one branch instructions. Two variations of branch instructions are: first one conditionally executed, that is it's having the limited range signed 8-bit immediate, that is range from -256 to +256 bytes. Second one removes conditional part of the instructions and expands effective range, that is effective range to sign 11-bit immediate, that is -2048 to +2046 bytes. Syntax for branch instruction: B conditional label, B label, BL label. BL instruction is not conditionally executed and has a range of plus L minus L to the 4 MB. It is possible because that is BLX instruction are translated into pair of 16-bit thumb instruction, that is branch link instructions. As shown in diagram, first instruction in the pair hold the high part of the branch offset and the second the low part. These instructions must be used as a pair. Example: move PC, LR, BX, LR, pop in parenthesis PC, that is program counter. To return, we set the PC to the value in link register, the stack instruction called pop operations. Second, data processing instructions. These instructions manipulate data within registers. It include move instructions, arithmetic instructions, shift instruction, logical instructions, comparison instruction, and multiply instruction. These instructions follow the same style as the equivalent ARM instructions. Most thumb data processing instructions operate on a few low registers and update the CPSR. The exceptions are move RD, RN, add RD, RM, CMP RN, RM, add SP, hash immediate, sub SP, hash immediate, add RD, SP, hash immediate, add RD, PC, hash immediate. It can operate on the higher registers, that is R8 to the R15 and the program counter. These instructions, except for CMP, that is comparison, do not update the condition flags in the CPSR when using the higher registers. The CMP instructions, however, always update the CPSR. As shown in syntax, we have used the ADC or add or AND or BIC or EOR or move or mul. EOR means exclusive or mul or MVN negated, that is NEG, ORR, ORing, SBC and or sub, along with the RD, RM. So this way we have to define here arithmetic instruction, logical instructions as shown in syntax. While right side is the descriptions of each instruction, that is ADC, that means add two 32-bit values and carry, and simple add, that is add two 32-bit values, while RD equal to RN plus immediate are described here in syntax. Again, this is a second table, and is logical bitwise and of two 32-bit values. ASR are for arithmetic shift right, BIC are used for logical bit clear and not, that is of two 32-bit values. CMN means compare negative to 32-bit values. CMP means compare two 32-bit integers. EOR means logical exclusive or of 32-bit values. So in this way we can define data processing instructions. There is one more table is define the data processing instruction, that is ROR, that is rotate right, SBC for subtract with carry, subsimple subtract, and last one test bits of 32-bit value. Next set, that is stack instructions. The thumb stack operations are different from the equivalent ARM instruction because they use the more traditional pop and push concept. Syntax here: pop in parenthesis low underscore register underscore list parenthesis comma PC that is program counter. Push low underscore register underscore list, comma LR, that is link registers. As shown in diagram, that is pop and push instructions are described here. Push means push register onto the stack, and pop means pop register from the stack. The interesting point to note that there is a no stack pointer in the instruction. This is because the stack pointer is fixed as a register R13 in thumb operation, and SP is automatically updated. The list of the register is limited to the low register, that is R0 to R7. The push register list also can include the link registers LR. Similarly, the pop register list can include the PC. This provides support for subroutine entry and exit. Last one, software interrupt instructions. Thumb software interrupt, that is SWI instructions, causes a software interrupt exceptions. If any interrupt or exceptions flag is raised in thumb state, the processor automatically reverts back to the ARM state to handle the exceptions. Syntax for software interrupt instruction, that is SWI immediate, as shown in diagram, that is SWI software interrupt with its register value. The thumb SWI instruction has the same effect and nearly the same syntax as the ARM equivalent. It differs in that SWI number is limited to the range 0 to 255 and it is not conditionally executed. As shown in diagram, it can separate on higher register, that is R8 to R15 and 14, and the program counter. These instructions, except for CMP, do not update the condition flag in the CPSR when using the higher registers. The CMP instruction, however, always update the CPSR. References I have used for this topic: ARM System Developers Guide, Designing and Optimizing System Software, Andrew N. Sloss, Dominic Sims, Chris Wright, Morgan Kaufman, publisher. Second one, Embedded System Architecture, Programming and Design by the Rajkamal, Tata, McGraw-Hill Education. Third one, Frank Wahid, Embedded System Wiki India, Willy India. Fourth one, Embedded Real System Programming, Ayar Gupta, TMH. Fifth one, Embedded System Software Primer, David Simon Pearson. Thank you.